Welcome everybody. I'm just going to hit record. Glad that people are enjoying the warm-up music. As always, feel free to let me know what your requests are in the comments. This morning we had some pretty cool jazz, so really enjoyed that. A couple of announcements before we start the lecture. Firstly, Monday is a public holiday in Sydney, but like someone said on the chat, because I love math so much, I'm going to do the lecture anyway. Okay, and so will Captain Bill. He will also do a lecture. And the reason is because if we don't do it on Monday, then I just have to do it at some other time. So feel free to join us or not. It will be recorded. So yeah, feel free to join us. In today's lecture, we're going to continue the calculus. So let me share my Chrome tab with you. So I think it's lecture number 7 for our calculus lecture. And we're going to look at 3 things. So split functions and differentiability. Okay, differentiability. We're going to look at how you differentiate relations or implicitly defined functions. And we'll also look at related rates. Now, some of this will be familiar. Probably the related rates will be familiar, but these two might not be familiar. Okay, so again, one of the nice things about calculus is some things will be familiar and some things will be new. Okay, all right, so let's get down to it. All right, so these are the parts to today's lecture. A couple of things to note. So for example, with implicit differentiation, if we had something like this, how do you actually find the derivative? Okay, so this is like a relation, and when we differentiate something like this, we talk about implicit differentiation. And with the split functions, remember, a split function is sort of something like this. It's defined in 2 parts, say. And what you want is to ensure that these 2 functions have a smooth connection, right? We saw an example, a related example in the previous lecture. And this one is mostly about the chain rule. Okay, we'll just touch on this. We'll see this more in the end when we look at mean value theorem. So don't worry about this bit too much yet. Okay, that's sort of just at the end. All right. So 3 things. One of the key things with this related rates of change is the chain rule. Okay, that's the really important thing. So the chain rule is sort of driving these questions, this part, and you can use sometimes you can use the second part in the third part. Okay. All right, so this is an important theorem. Okay, usually in mathematics courses, when you see a name, like a theorem with a name, like intermediate value theorem, it means that it's so important that we give it a name. Okay, so this is another one of these theorems. All right, it's called the split function theorem, and it's related to differentiability. Okay, So what the split function theorem tells us is if these conditions hold, then your split function is actually differentiable at the point where the definition changes. But it's quite a long theorem, so let's walk through it together, and we can work it out. Okay, so we know that a function is differentiable at a point A if this limit exists, right? But it's not always easy to work this out, or it's actually quite time consuming. So the nice thing about this split function theorem, or SFT, is that it can save you a lot of time. Okay, so let's walk through the statement, and then we can see it in action. Okay, so let A be a fixed number and consider a split function f. So the change happens at the point A. If the two parts are differentiable and their derivatives at the point A are equal, and this function is continuous at A, then the split function theorem tells us that the function is differentiable at the point A. Okay, so let me, that's quite a significant theorem. So let me just repeat that, okay? You've got two functions, and you're assuming they're differentiable and continuous, right? Because the differentiability assumes they're continuous. And in particular, that these two derivatives are equal. If that's true and the function is continuous at A, then the conclusion is the split function is differentiable at A, okay? So this is quite a difficult theorem. So don't worry if it's like, well, what does that mean? You'll see it come together when we do an example, okay? But this is an important theorem that will expect you to know and to refer to or draw on when you're doing your assessment, okay? So quite important. All right, so this is a classic example. All right, you've got a split function. It's a quadratic equation for a quadratic function for x less than 2, and it's some kind of linear function for x greater than or equal to 2, okay? So this would be your, in this setup, this function would be your p of x, a would be 2, this would be your q of x, okay? And what you're asked to do there is to find values of c and d, if any, that will ensure the split function is differentiable at x equals 2. So you've got a nice smooth join between those two functions at the point x equals 2. Okay? So you can do that, the split function theorem. Okay? All right, so how do we do it? Well, there's two things to calculate, c and d. We don't know what they are, but we can use this and this to get both C and D. Okay, so probably the easiest is to do this first. Okay, that'll give you either C or D, and then the continuity will give you the other part. Okay, so the idea is to apply the SFT, the split function theorem. All right, okay, so this is a polynomial, this is a polynomial. So they're so both of the parts are differentiable and continuous. Right? So good question, Abdul Rahman. Let's look down further into that. We want C to be a constant, right? Okay, so that's a quadratic, that's a linear function. They're both differentiable near the point where the thing changes. Okay, so now let's consider this. So if we differentiate that, yeah, Matthew's on the right track, we'll get negative 2x, and we want to evaluate that at x equals 2. So that's going to be negative 4. And let's work that out with q of x and compute the derivative. And if we differentiate that, we just get c. So if we want this to hold, we need these two things to be negative 2, sorry, negative 4. That should be a negative sign. Okay, c equals negative 4. Yes, people are, Junsheng in the chat is saying, so for this to hold, we need c equals negative 4. Which piece of paper, Daniel, the top one or the bottom one? Down. Yeah, but I can't actually do the thing. Okay, so like I can't actually write and have that in the same thing. Okay, so at the moment, that's the best I can do for you, Daniel. Sorry. Okay. Yeah, you should have the notes in front of you, right, on a PDF or something. But I'll move that down a bit more. All right, so we know that C would be equal to negative 4. Let's find D. Okay, so from the continuity. X equals 2. Okay, oops, sorry, now I've got to move it up. Okay, so in order for this function to be continuous, we want the limit at x equals 2 to equal the value of the function at x equals 2. Okay, so that's how we're going to do it. All right, so the limit all right, so what is f of 2? Who can tell me in the chat? What is for this split function, what is f of 2? Who can tell me in the chat? Who can tell me? Anyone? Now we know c is negative 4, right? So you're going to get negative 4 times 2. Something like that, right? Is that right? Let me just check. Yep. Okay. So now let's take these limits, right? So, and we'll take, what's the limit going to be as x approaches, say, 2 from the left? Okay. So it's going to be 1 minus x squared. So that's just a polynomial. So we can just put that in. And you're going to get 1 minus 4 equals negative 3. Okay. So we want those two things to be equal. You can check the right-hand limit, but that's enough. So we want that to be equal to that for the continuity. Okay. So if those are equal, we can say D equals, what's D going to be? 5. All right. So we've got C equals negative 4, and we've got D equals 5. Okay, so let's make our conclusion by the split function theorem. C will equal -4, D will equal 5. All right. All right, so there's a few questions in the chat. Thank you for putting in the suggestions. So Azalea is asking, is this theorem saying that f is differentiable at x equals a? Yes, that's correct. No, not if and only if, Azalea. Okay, that's a really good question. It's not saying if and only if. This is just an if-then statement. Okay, so it doesn't work both ways. Really good question. Okay, so if the conditions of the split function theorem are not satisfied, then you can't say anything. Okay, then you can't say anything. All right, so really good question though. Okay, so that would be the conclusion and the answers. What does this look like as a picture? Okay, what does this look like as a picture? Because some people will want to actually see, well, what does this actually mean, Chris? Okay, so let me just go back here and let me see if I can. Oh, yes. What does this mean as a picture? I'm confused. Yeah, I'm confused too. All right, let's have a look at GeoGebra, shall we, and see what happens. Okay, sounds good. So let's have a look at GeoGebra and we can draw a picture. All right, so here is 1/2 of our split function. Okay. And here is the other half with C equals -4 and D equals 5. Now, if I zoom in here, that's a super smooth join, right? That is a super smooth join. And you're going to get a nice tangent line there. Okay. In the previous lecture, we saw places where they had sharp corners and no tangent line. You couldn't draw a tangent line, but here you can. Okay. So even though this is a quadratic function and the one on the right is a linear function, you can still join them in a way where you get the nice smooth join. Okay. So that's kind of what you're looking for when you're doing these problems. Now, these are not particularly easy problems, and students get confused because they're not sure what they're calculating, right? So let me just step you through it one more time. Oh, let's get away from the plushies. Okay, so the first, we want to calculate the values C and D, okay? The first one, and we apply the split function theorem. The first thing is to get these two things to be equal. That gives you one thing. The second is to employ the continuity, okay? That gets you the other value. Now, if you're ever worried or not sure about your solution, you can always plot a picture. Does the join look nice and smooth? Okay? All right. So that's the split function theorem. The proof is in your notes. I won't discuss a proof in this lecture. It's probably beyond the course. But let's move on now to implicit differentiation. Keep going in the chat, everyone, and let me know if you have any comments or any questions, or if I'm not being clear about something. This is quite a challenging theorem. So, don't worry if it's not obvious at the moment, okay? So this and this ensures you've got a smooth join. That's kind of it. That's what it really means. All right, so implicit differentiation is a little bit easier than the split function theorem. As we probably know, you can have these equations where instead of having this, you have this, and y is a function of x. Now, one of the nice things with this is that it's more general and you can do more things with it. Okay. So this is like a more general equation. And what we're going to do is explore how to compute the derivative of these more general equations. Now, some of you may have seen this before, okay? And if you've seen it before, great. Okay, so let's just have a look at the idea. So this is the equation. We call it an implicit equation. And the most important thing here is to use the chain rule and any and possibly other rules. And rearrange. All right. So there's a definite strategy with these ones. Okay. And I'll show you by the by using an example. Okay. Because I think most people learn by examples. All right. So let's say I had something like this, right? I wanted to differentiate something like this: sine x minus 4xy squared plus 1 equals 0. Okay. So that would be your implicit sort of the f of xy in this case. So how do you differentiate it? Well, I'm glad you asked. I'm glad too, yeah. The idea is you differentiate both sides, okay? And you can use the chain rule or the product rule or something to simplify this and then rearrange, okay? But let me show you, because usually the examples are the most interesting and the places where people learn the most, okay? So this is a classic example. Compute the derivative from this implicit equation. So over here, this would be your function, and we're assuming that y is a function of x, all right? That's sort of just, we're kind of assuming that. All right, so how do we do it? Well, it's not difficult, and there's a definite strategy to computing these things, right? Differentiate both sides. So let's differentiate okay? So this is nice because we can break it up into, you know, the derivative of that plus the derivative of that minus the derivative of that, etc. Oops, sorry, that shouldn't be there. All right, so we are differentiating both sides with respect to x. Great. Okay. So let's break this up into parts. If we differentiate y with respect to x, that's all we can do. We can't simplify that any further. This one's a bit different though. So I'm just going to leave that and I'll come back to that. Okay. If we differentiate negative x cubed with respect to x, we get negative 3x squared. And if we differentiate 4x with respect to x, we get 4. And if we differentiate 0, we get 0. So the only difficult thing here is differentiating this. Okay? Now, this is where the chain rule can come in. Okay? This is where the chain rule can come in. Okay? So what I'm going to do is play with the derivative and involve the chain rule. So watch what I do. Okay, so because we're differentiating with respect to x there, and there's no x there, what I've done is I've kind of multiplied here so I can get that d dy of that, okay? So you can see it's the same as d dx, but if I add those extra differentials in, I can just do that. Yeah, Abdul Rahman, exactly. Okay, so this is just the chain rule going on here, right? Do, 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 do. Now you see it, now you don't. So if we differentiate with respect to y, this is just going to become 2y. So I can say by the chain rule. Okay, and so now this is going to become 2y. All right, so we're going to group these together, rearrange and make dy dx the subject. This is the very last step in the process. So we want dy dx equals something. So last step, rearrange. So we're going to get dy dx times 2 plus 2y. And let's take those two terms to the other side. And now we can just divide out, okay? That's it. Okay. Yep. Just made a mistake in my notes here. Minus, plus. Okay. So there it is. Amazing. Now for these kinds of problems, the strategy is usually the same, right? You differentiate both sides of your equation. Look at where the functions of y are and use the chain rule to manage those derivatives. Group the derivatives together and rearrange. Okay? So Nick, right here, Nicholas, right here. So d dx is dy dx times d dy. It's just here, right? If I cover that up, that and that are the same. Okay? So from that step to that step, that's where we're invoking the chain rule. It's a good question, and it's really a fundamental part of the problem solving. So it's a really good question. Okay, so that's one example. I think this is so important that I want to do another example, because this is like an entry level type problem, and sometimes you'll get something that's a bit more complicated. All right, so let's do another one. The steps are the same. It's just getting to this part, right? Here we just use the chain rule, but sometimes you use some other rules as well as the chain rule. Okay, so I think that's really important to investigate. All right. So this is a bit more challenging, this problem. So again, we're assuming that y is a function of x. This would be your actually, I'll rewrite that. You can think of this as your function here. Okay. The constant over here doesn't really matter, because when you're differentiating both sides, you know, if it's 0 or 1 or whatever, it's still going to go to 0 when you differentiate it. So don't be too worried by the constant over here. But let's do it again and see if we can do it. It's similar to the previous example. All right, so let's do it. So consider, please. All right, so standard rule, we're assuming this, we differentiate both sides, and we need to somehow work this out, and obviously this is simple, okay? Now, if you look closely, this and this, they're both products, right? That's x times y, and this is x squared times y squared. So if we're going to differentiate these, let's use the product rule. So we're going to use the chain rule and the product rule, okay? So let's work that out first. So let's do the chain rule first on this one, okay? So it's going to be x times dy dx plus y times d dx. Okay, so that's the product rule for the first part, plus okay, so we've used the product rule on that, and we've used the product rule on that. Okay, so we've done the product rule twice. Okay, so now we have to work out that which is easy, that which is similar to the previous problem, and that which is easy. Okay. So let's see what we have. So the derivative of x with respect to x is just 1. Sweet. The derivative of this, well, that's going to be more difficult. The derivative of this is just 2x. So let's work this out. Yeah, I can do that. So it's going to be dy dx times d dy of y squared. Okay, that extra bracket, you don't really need that. And what about this one? So the derivative of x squared with respect to x is just 2x. So now all we need to do is simplify this. That's going to become 2y. So dy dx times 2xy. And I've got this down here. All right, so it took us an extra step, but now we're kind of in this stage where we want to group the derivatives together and rearrange. Okay. So we factor out the dy dx's, move the other terms to the other side, and then divide. Now we're going to get a pretty messy derivative, but that's okay. So these questions, they're not difficult, they're just a bit longer than x squared, correct. Thank you. See how easy it is to make a mistake? So that x squared Hang on. So if I differentiate that, I get 2yx squared. Okay, so that's just a 1, 2y x squared. Okay. Okay. Okay, have I got that right now? Oh, hang on. I should go in here. Oh, I messed that up. Hang on. Let me just redo that. Hang on a sec. So let me just come in there and do that again. Okay. It's like the mistake never happened. Okay. Haha. So okay, so that's going to become 2y. All right, hopefully that's correct. Okay, so if I differentiate that, I'm going to get 2y. So I'm going to get that, and then I can factorize that. Let's see if I can get this correct. Move those to the other side. And now rearrange. I think that looks better. Okay, so let me know if I've made a mistake there or if I've got the calculations wrong. I think I just put the index in the wrong spot there. So let me just triple check that. Yep, I think that's okay. Yep. Oh, oh, phew. Yeah, I was a bit worried there for a minute. Yeah, I was a bit worried too. Me too. Okay, so anyway, thanks for pointing that out, everyone. Sure, it's a good question. Do we always have to write down the chain rule? Part of the justification, I guess, relies on the chain rule. If you're like when you do your final exam and stuff, you'll be asked to show some working out. You can either refer to it. I like to put it in, but it's up to you really. I would write more rather than less because the person who's marking your work doesn't always know what you're thinking. Okay, so I would just refer to the chain rule or explicitly write it, but it's up to you. It's up to you. Okay. You can see from, I made a little mistake there. You can see how tricky it can get, right? So don't underestimate it. All right, a little thing on related rates here. And again, I think some of you will have seen these problems before. So the idea is sort of more kind of applied problems. And one of the nice things here is to draw on the chain rule. Okay, so I'll show you an example of a related rate problem in a second, but basically you're asked to compute some rate of change that's not easily measurable. Okay, and you essentially use the chain rule and some manipulation to get what you want here. And there's a standard strategy with these kind of applied problems where you want to draw a diagram, write down the given information and what you want to compute, relate the variables through some sort of equation, differentiate, also use the chain rule, and then evaluate. So this is a nice kind of structure for solving these problems. But you know, it's more about guidelines than hard rules. But this is just a nice summary regarding strategy. So let me show you. All right. So this example is a classic problem, right? You've got a balloon that we assume is a sphere, and you're told that the volume is increasing at this rate, 5 pi cubic meters per second, right? And they're asking you, what is the rate at which the radius is increasing when the radius equals 25, okay? So let's see if we can work through this, and we'll draw on some of these strategies here. Okay, so draw a diagram, all right? Let's do that. So this is going to be my badly drawn balloon. Okay, looks more like an egg than a balloon, but anyway, we'll assume it's a sphere. And we'll let the radius be r. Okay? And I'm going to introduce some notation. R is going to depend on time. And I'm going to let V be the volume. Now I know that there is a connection between the volume of a sphere and its radius. Okay? This is what we're going to do in step 4 when we relate the variables through an equation. Okay? So we're given that the spherical balloon is being inflated at this rate. So we know that dV dt is 5 pi meters, cubic meters per second. And we want the rate at which the radius is increasing when radius is 25 meters. So we want dr dt when r equals 25 meters. Okay, so that's the initial data. That's what we want. Here's a diagram with some labels and some notation. Let's relate the variables through an equation. Okay, so we know that V equals 4 on 3 pi r cubed. So that's the relationship between the volume and the radius. Okay, so we want that. We've got that. What we can do is use the chain rule on here to get the derivatives that we want. Okay, so this is a critical step. So dV dt equals dV dr times dr dt. Okay, so dV dt is given there. dV dr and dr dt is there. Okay, so can we compute dV dr from that? Of course we can. So I differentiate this with respect to r, it's going to be 4 pi r squared, okay? All right. So, Anubhav, you've already solved it. Let's have a look. See if you're correct. Okay. Okay, so we're going to, if you combine things now, let's do it. dv dt is going to be 5 pi. That times dr dt. So now, oh, sorry, let me move that up. So now let's isolate that, rearrange, and we can compute dr dt when r equals 25. So this is the last step. So obviously the pi's are going to cancel. And I want to put in r equals 25. Okay, so last step. So it's going to be 5 on 4 times 25 squared. Okay, so 25 squared is the same as 5 to the power 4. Yep, so So 5 cubed is 125 times 4 is, hello, Colleen. And that's going to be 4 times 125, which is 1 on 500. So this will be in meters per second. Okay, welcome, Bill, Captain Bill. All right, so like they're fascinating problems, these ones, and you may have seen them before, but I find that these strategy steps can be quite helpful, right? Just to clarify your thinking, but also as a guide with a steps and a checklist, right? So you can see we drew a diagram, we introduced some notation and some labels. We clearly identified the given information and what we wanted. We came up with an equation linking the variables, and we employed the chain rule. Okay. Once we did that, it was just a matter of rearranging and plugging in your question. Okay. Abdul Rahman, I'll go back to that for us in a minute at the end. Okay. Is that okay? Because I'm sort of running out of time. All right. So there you go. So that's a classic example here. And the very last thing that I wanted to discuss with you was these error estimates. I don't want to go into too much detail there, but we're going to see more detail when we look at the mean value theorem. So I don't really want to talk about this too much, okay? But essentially it involves approximating functions by a tangent line, right? Or curve. So if I've got, say, a graph like this, and this is some point A, what this tells me is that if I draw a tangent line to that graph, and I'm, say, over here, the difference between the value of the tangent line and the value of the graph isn't going to be great. Okay. So using, and this funny squiggly equal sign means is approximately equal to. Okay. So as a really super simple example, and like I said, I don't want to spend too much time on this. suppose I want to estimate that by that. Okay, so we can put in this square root function. So that would be your f, and your a would be 16. Okay, and so what this means here is that the square root of 16.01 is approximately equal to this. Okay, and so if you want to sort of move this around, you can say, oh, well, the error or the difference between what we want and what we can compute, well, that's going to be, that's going to be 0.1 on the top. This is going to be 8. And so this is basically 1 on 800. So if we wanted to, say, approximate this thing that's hard to calculate by this thing that's easy to calculate, the bottom line tells us that the error between our calculation and what we really want is pretty small, right? It's pretty small. Now, so 2 things for that slide. Tangent lines can provide a good approximation as long as you don't wander too far away from the point where they touch. And we'll see more in detail when we look at this thing called the mean value theorem. The mean value theorem. Okay, so don't worry too much about this yet. Abdul Rahman, you wanted me to go back. Let me hide my little mistake here. So was there anything you wanted to ask about in particular? If not, I will sign off, people. So let's see if we can simplify it. Can we simplify it? See if you can simplify it, Abdul Rahman. Let's see if we can simplify that. So you've got a common factor of y on the top. Okay, I'm just doing some calculations here. And you've got a common factor of x on the bottom. Oh yeah, it looks like it's going to simplify nicely. Okay. So you can simplify that as long as x 2xy does not equal -1. Okay, so you can actually factor that out. Good spotting, and simplify if you wanted to, and as long as you're not dividing by 0. Okay. Excellent. All right. Thank you. All right, everyone. I've gone a couple of minutes over. Sorry for that. I'm going to turn on microphones and stuff if people want to chat or share their video, whatever. Yeah, let me know what you think in the chat or ask some questions. Remember, Monday's tutorial is on like Donkey Kong. What did Bill say this morning? Kick those tires, light those fires. It is on. We love maths too much. Okay. Thank you, Nathaniel. Let's go. What do you guys think? Oh yeah, we're really hyped to be giving a lecture on a public holiday. Me too. Are you crazy? I think they're crazy. Yeah, I'm crazy. Anyway. So I'll hang around for a few minutes. And yeah. If you have any questions, let us know. Let us know. I don't know if anybody can hear my kids. They're screaming in the background. Let me know if you can hear my children. Yeah. I might just say something. Oi, my students say they can hear you. Be quiet. We can't interrupt the really important maths. I know. At some point, you'll probably get to see my children. Sometimes they just wander in. I'll get them out. Hey, Chloe, you want to come in here? Say hello. Okay. Come on. Come and say hello. There's 93 people here. So this is Chloe. She's my daughter. You want to come in and say hello? And this is Alexander. Let me just get that up a bit. This is Alexander. He's Chloe's friend and schoolmate. Hello.
Hello.
So there's like
I can't see anybody.
No, I can't. Like they can. Like they haven't got their cameras turned on.
Yeah.
But yeah.
We're not seeing anybody.
Yeah, I know. So anyway, I've got Plushie Cam. Did you see Plushie Cam, Chloe? So I've got anyway. All right, ciao. Anyway, they say hi. Yeah, cool hat. Agree. That's a Wallara public school hat, even though no one goes to school. All right, thank you, everybody. I will sign off and see you later in the tutorials, maybe later on today.